Hello students, welcome to the class. So in the previous class, as I said, we'll be starting with resonance structures. We had finished up to bond order and how these all are bond energy, bond parameters we had completed. And we have seen how they are interrelated to each other. Moving to the next concept, that is resonance structures. Okay, this resonance structure, the concept of resonance, the phenomenon of resonance, it was put forward by Heisenberg. It was put forward by Heisenberg to explain the properties of certain molecules. Okay, to explain the properties of certain molecules. So what are resonance structures? See, what happens is, in case of certain molecules, a single Lewis structure, we know how to write Lewis structure, right? Yes, a single Lewis structure cannot explain all the properties of the molecules. It cannot explain all the properties. Like for example, if I say carbon dioxide, in the last class only we have seen, this is the structure for carbon dioxide, right? Here there are two lone pairs, here there are two lone pairs. So this is the structure which explains the entire properties of carbon dioxide. But in some other molecules, a single structure, like if you take example of ozone, a single structure cannot explain all the properties of the molecules. Yes, thus the molecule is then supposed to have many structures, each of which can explain most of the properties of the molecule. I cannot say that it will explain all of the properties. So each structure will explain most of the properties of the molecules, but none can explain all the properties. For example, I'll take ozone only I will consider. We will calculate T, we will calculate V, we will calculate S, and we will calculate U. That is shared electrons, unshared electrons, total electrons. Ozone, so 8 into 3. There are 24 electrons. Then valence electrons on oxygen are 6. So 6 into 3, it is 18 electrons. So 24 minus 18 is 6 electrons. And 18 minus 6 is how much? 12 electrons. So with this, when I try to write the structure for the ozone molecule, actually ozone has got ozone has got a bent structure. So if I want to represent ozone, how I can represent is, I will write 3 oxygen atoms in this inverted V format. How many shared electrons are there? 6. Therefore 1, 2, 3, 4. One more has remained. See, I can write that shared electron here, or I can take it like this. And I can write, so 1, 2, 3, 4, and this shared electron I can write it here. That means a double bond between these two oxygens may occur, and here is a single bond, or there will be single bond this side and a double bond may occur on these two oxygen atoms. Depending on that, we will balance the remaining valence electrons, correct? Lone pairs of electrons. So here 4 will come, here there will be only 2, and here 3 lone pairs will come, correct? Similarly, here 3 lone pairs will come. Here there will be only 2, and here 2 lone pairs. So 2 lone pairs will come. So see, oxygen molecule, it can be represented by more than one structures, right? You can represent it by more than one structures where there is movement of electrons, these electrons, right? We call it as delocalization. So when certain molecules are represented by more than one structure, each structure will tell some of the properties. Yes, and you cannot say that entire structure will give us all the properties. Yes, so none of the structures will explain all the properties of the molecule, of a compound. That time what we say, we consider the actual structure is in between all of these contributing structures. So this is contributing structure and this is also contributing structure. So actual structure is the in between all of these contributing structures, and I will write it as oxygen, oxygen, oxygen atoms. Single bond is existing. Double bond can be either here, I will denote it as a dotted line, or it can be either here, I will denote it as a dotted line. Understanding? Yes, are you all getting it? This is called as resonance hybrid. What it is called as resonance hybrid. And the different individual structures, they are called as, you can call it as resonating structures, or you can call it as canonical structures. Canonical structures. And it was for the first time given by Heisenberg. It was given by Heisenberg. And this phenomenon is called what? It is called as resonance. So this is a small illustration to explain here. So you can see here oxygen, I can represent, ozone, I can represent it like this. I can represent it like this. So as of resonance hybrid, when you take what is the original structure, we say the actual structure lies in between these structures. These are called resonating structures. You can call them canonical structures or you can call them contributing structures also. Yes. So actual structure will be in between these structures, and that is written like this, wherein double bond can be at this between two carbon atoms, oxygen atoms, or it can be between these two oxygen atoms. And that actual structure we call it as what? We call it as resonance hybrid. So as a resonance hybrid of about two structures, for simplicity, ozone may be represented like this. You can represent it like this, which shows resonance hybrid having equal bonds between single and double bonds. So there is equality. Okay. So resonance is shown in different molecules also. It is shown, one more example what you can take is, it is shown in benzene. It is shown in toluene. These are the molecules where resonance is shown. Yes. So as the result of resonance, what happens is, see, as I said, we were speaking in the previous class, we were speaking about bond order. That is the bond between the two combining atoms. Okay. The combining atoms may be same or they may be different. How many bonds are there? That is the bond order. Suppose there is one bond, we call bond order equal to 1. 2 bonds, we call bond order equal to 2. 3 bonds, bond order equal to 3. Maximum is 3. And minimum is 0. 0 means what? No bond exists. And that molecule does not exist. It means, okay. Now see, as bond order increases, what will happen? I said, the atoms or the combining particles will come closer, correct? So when they come closer, the distance will, what will happen to the distance? The distance will decrease. So when I compare single bond distance and the double bond distance, it will differ. So this bond length will be more compared to this. Yes. So we have said it, as bond order increases, bond length decreases. Bond length decreases. So this bond order will be less and this bond order will be, this bond length will be least. Understanding? But here, as the result of resonance, the bond lengths of single bonds and double bonds in a molecule become equal. They become equal. So that is the explanation of resonance. So what, if resonance wasn't there, if you would have considered this molecule, this structure as a structure of ozone, then here we would say this bond length is less and this bond length is more. Here we would say this bond length is more and this bond length is less. Understanding? Are you all getting it? But with the concept of resonance, with the introduction of the resonance, or as the result of resonance, whether it is a double bond or a single bond, all bond lengths will be same. The bond lengths will be equal. The bond lengths will not vary. You cannot say, in case of resonance, you cannot say that the bond length is different for single bond and it is different for double bond. No, the bond length will be same, whether it is single bond or it is double bond. Are you all getting? Are you all understanding what I'm trying to say here? Yes. Okay. Next point, what I want to say is the resonance hybrid. The actual structure is resonance hybrid, I said. Okay. Why I said this as the actual structure? Might be it is very stable. Yes or no? In chemistry, whatever we speak about is most to be existing is because of its stability. And when a compound becomes stable, when it is having lower energy. So please do remember, this works in resonance also. These are resonating structures, okay, or canonical structures. And the actual structure lies in between them and it is written like this, which is called resonance hybrid. Resonance hybrid, what it is formed, it will have, why it is said to be actual structure? Because it will have lower energy. It will have lower energy and hence what? And hence greater stability. And hence greater stability. Are you all understanding? It will have, resonance hybrid will have lower energy and hence greater stability as compared to the contributing structures or the canonical structures. Okay, this is first point regarding, so I've said first point, resonance hybrid will have lower energy and hence higher stability than canonical structures. Second point is, for a given molecule, as number of resonance structures or canonical structures increase, as the number of resonance or canonical structures increase, what will happen? Greater the number of canonical structures, especially with nearly same energy, canonical structures are expected to have nearly same energy, then greater is the stability of the molecule. Greater is the stability of the molecule. Greater is the stability of the molecule. Therefore, I can say with more number of resonance structures, greater will be the stability of the molecule. And those resonance structures should have almost same energy. Okay. Now, what is this resonance energy? Yes. Difference between energy of resonance hybrid and the most stable resonance structure. See, we have got resonance structures, canonical structures, and we have hybrid. So, difference in energy, or let me write it like this, resonance energy is equal to energy of resonance hybrid minus energy of most stable resonance structure. Most stable resonance structure. That is nothing but resonance hybrid. Resonance energy. So what is resonance energy? Energy of the resonance hybrid minus energy of most stable resonance structures. Yes. Now, what are the conditions? Looking at the molecule, how can we expect that it will have a resonance structure? Conditions for writing the resonance. They should have same atomic positions. Their atomic positions must be same. They should have same number of bond pairs and lone pairs. You cannot write any number of bond pairs and lone pairs and say it is a resonance structure. Okay. Next, all the resonance structures should have nearly same energy. They must possess nearly same energy. They should have nearly same energy. Okay. They must possess nearly same energy. They should be written such that negative charge is present on an electronegative atom and positive charge is present on an electropositive atom. See, when you're writing resonance, you should be very careful. The negative charge should come on electronegative atom. The positive charge should come on electropositive atom only. You cannot do vice versa of it. The like charges should not reside on adjacent atoms. They should be far away. Unlike charges should not be greatly separated. Yes. Now, in case of molecules or ions having resonance, the bond order changes is calculated as. So when there are resonance structures, the bond order changes, and the formula for bond order is total number of bonds between two atoms in all structures divided by total number of resonating structures. Yes. So between two atoms in all structures, you see total number of bonds present, and divided by total number of resonating structures will give you bond order. When I take the examples, I'll show you. Okay. So resonance structures are the sets of Lewis structures that describe the delocalization of the electrons in polyatomic ions or molecules. Resonance in chemistry could be a manner of describing the bonding in particular molecules or ions by merging many contributory structures or forms jointly called canonical structures or resonance structures within the theory of valence bonding into a hybrid resonance, which is called hybrid structure. So here you can see this is the structure of resonance hybrid. Structure of resonance hybrid. The different resonance structures, these are the different resonance structures For which ion? Carbonate ion, CO3 minus 2. So these are different structures. You can see their positive charge is on electropositive atom, negative charges are on electronegative. They are not separated very far. Yes. So I can shift this double bond here also. I can get the double bond here also. So depending on that, I have different structures. And these are called what? These are called resonating structures, or they are called resonance hybrid. Sorry, they are called canonical structures, or they are also called contributing structures. So what are the names? They are called resonance structures, or they are called canonical structures, or they are also called contributing structures. And the actual structure lies in between all of these, and that is nothing but resonance hybrid. That is nothing but resonance hybrid. Yes. So resonance hybrid. And how do you find resonance energy? The energy in resonance hybrid minus the energy in most stable structure, resonance structure. So the delocalization of electrons is described via fractional bonds, which are denoted by dotted lines here, and fractional charges in the resonance hybrid. So these are all fractional charges. Yes, sometimes resonance structures are not equivalent, and it is important to determine which one best describes the actual bonding. So if you want to describe best actual bonding, formal charge you can use. And you know what is the formula of formal charge. Yes, what is the formula of formal charge? We have seen a formal charge is equal to V minus L minus half into S. You can calculate formal charge on all the atoms, and then you can speak about the resonance structures. You have for the certain examples I have. First one, resonance structures of NO2 minus. So NO2 minus. So this is called nitrite ion. So in a nitrite ion, the bond lengths of both nitrogen oxygen, there are two nitrogen oxygen bonds, and I need not explain you how to find Lewis structure. Yes, Lewis dot structure of NO2 minus you already know. What it highlights, a difference in bond order of the two bonds. So here NO2 minus Lewis structure I will write. So this is the structure, Lewis structure. Yes, this can be also written as correct. It can be also written like this. And remember, resonance structures are separated by this arrow mark. This arrow mark. They are separated by this arrow. Okay. So these two are what? These two are canonical structures, or they are also called resonating structures. Okay. So if you want to write the hybrid is separated by this symbol. So I will write N. Single bond is common in both the cases with oxygen, and there is double bond character here, or there is double bond character here. Correct. So if you see the bond length of both of them, this bond length is also 125 picometers. This bond length is also 125 picometers. Both bond lengths are same, 125 picometers. Yes, understanding? So resonance hybrid suggests that each oxygen atom holds partial charge. It holds partial charge. So each oxygen atom holds partial charge. If you write formal charge, you will get to know on which oxygen there is charge. Yes. So here it is on this oxygen. Here it is on this oxygen. Resonance hybrid says that each of them carry partial charge. And bond length is what? It is 125 picometers. One more example. You can take NO3 minus ion, which is called nitrate ion. Yes, it is called nitrate ion. So I know that by Lewis representation, I know how to write the structure of nitrate ion, NO3. There is a double bond character here, two electron pairs. Here there will be only two pairs. Here there will be two. So this is how we write nitrate ion, and here I'll write minus sign. I'm sorry. Okay. So when this can be represented like this also, I can represent it as N double bond over here, oxygen, single bond, oxygen, and the remaining lone pairs. Or I can represent it like this also, N single bond, here double bond, oxygen, single bond, oxygen. Yes, I can represent it like this. These are the resonating structures. When I want to write the hybrid, how can I write it? Nitrogen, here there is oxygen, here there is oxygen, here there is oxygen, and there is partial double bond character here, partial double bond character here, or partial double bond character here. Yes, understanding. So it is nitrogen is the central atom in nitrate ion, and it is singly bonded to oxygen, two oxygen atoms, and there is a double bond in all these three cases. When I want to write the hybrid, I will represent it like this. We'll represent it like this. Nitrogen is having positive charge. In this case, the single bonded oxygen atoms will have negative charges. Here, these two oxygens will have negative. Here, these two oxygens will have negative charge. Yes. Similarly, we have seen how to write the resonance structures for ozone. Carbonate ion we have seen. Yes, it is the common polyatomic ion found in limestone, baking powder and all, right? Baking soda. What is limestone? CaCO3. Baking powder, NaHCO, baking soda, NaHCO3. Yes or no? So this you can write the structure also, carbonate ion structure, right? Try to find the structure and then give different ways to represent that carbonate ion. Yes. So this is all about resonance. Even the best example what I can give you is about benzene. Yes. I can represent benzene structure. Here there are three bonds. I can represent it as, so this electrons may shift here. So negative charge is created here. Then bonds are there. Positive charge over here. So this electrons will shift here. This will come here. Then again, here bond is there, here bond is there, here positive charge as usual, here negative charge is created. Again, this negative charge shifts here. There is shifting of these electrons on this carbon. I'll explain you when you come to organic chemistry, this part very clearly will understand. Again, this electrons shift here. So I will get a structure where here there is double bond, here there is double bond, here there is double bond. So these are all what? These are all resonating structures. And the actual structure, yes, I need not represent it like this. How do I represent it? We'll write it like this. Yes, actual structure, what is happening? The double bond is, oh, there is double bond character here, there is double bond character here, double bond character here, double bond character here, double bond everywhere. So this is how we write the actual, this is called resonance hybrid. This is called resonance hybrid. So you can, or it is written like this also. Yes, this is written like this also. So this is resonance hybrid. So benzene molecule, it is stabilized by resonance, and these are all what? These are pi electrons we call. They are delocalized. They are delocalized, and you can see all the bond lengths. Here double bond, so bond length is less. Here single bond length is more. No, all the bond lengths are same. All the bond lengths are same. Yes. So this is about few examples on resonance structures. You can see a carbon dioxide, we can write it like this, we can write it like this. Carbon monoxide can be written like this. Nitrous oxide, resonance structures. Nitrous acid, HNO2, resonance structures. Hydrazoic acid, HN3, not NH3. NH3 is ammonia. It doesn't have resonance structures. Hydrazoic acid. Nitric acid, HNO3, can be written with resonance structures. So this is all about the resonance and resonance structures and resonance hybrid. Correct? Okay, moving to the next concept, that is polarity of bonds. See, we have already discussed about what is covalent bond. Correct. So we know what is covalent bond. Covalent bond is formed by mutual sharing of electrons. If the mutual sharing is between two same atoms, then electronegativity difference is 0, we say. If the mutual sharing is between two different atoms, then we say electronegativity difference is less. It cannot be more. So depending upon this, we have under covalent bond, we have two types of covalent compounds. If the electronegativity difference is entirely zero, it means what? The bond is between two similar atoms, and you call it as a what you said, homoatomic molecule, right? So if such compounds are said to be non-polar covalent compounds. Non-polar covalent compounds. Okay, they are said to be non-polar covalent compounds. Fine. If the electronegativity difference is there and it is less, then such compounds are said to be polar covalent compounds. Polar covalent compounds. So polarity means what? Polarity means what? It is a state or a condition of an atom or a molecule having positive and also negative charges. So especially in case of magnetic or electric poles. See, I did not speak about this concept in ionic bond, because in ionic bond already charges are there. We know it. It is a polar compound only. Ionic bond has got ions. So positive ion, negative ion, so polarity is there. So polarity is what? State or a condition of an atom having charges. It might be positive, it might be negative. What about covalent? Covalent bonding means, we have said, it is a mutual sharing of electrons. When mutual sharing is there, from where you will show the charges? There is charges present. That is understood from these two types, non-polar covalent compounds and polar covalent compounds. If the electronegativity difference is entirely zero, that means the bond is formed between two similar atoms. Such compounds are said to be non-polar covalent compounds. Examples: your H2, your Cl2, your N2, your O2, F2. These are all non-polar covalent compounds where electronegativity difference is entirely zero. Polar covalent compounds, example HCl. Yes, is this an example or no? Yes, it is an example. Yes, there is covalent bond only, but there is slight polarity. How do you explain it? Because chlorine is more electronegative than hydrogen. So what it will do? It will pull. I'm not saying it will take. It will pull electron pairs slightly towards itself. So when I show a bond, I will show it like this. Yes, I will show arrow mark like this. So it is pulling electron pair slightly towards itself. So when it is pulling electron pair slightly towards itself, there is electron density slightly more on chlorine and slightly less on hydrogen. That slight is denoted by this symbol. Yes, so delta. So electron density is slightly more on chlorine. So slightly more, delta minus. It is slightly less on hydrogen, delta plus. See students, there is a lot of difference between NaCl plus and minus, and HCl, delta plus and delta minus. Understanding? Here plus minus means what? Unit charges they are, which are formed by complete transfer of electrons. Delta plus delta minus means what? They are slight charge, partial charges they are. What they are? Partial charges. And those arise when there is slight electronegativity differences. So partial negative because shared electrons are being pulled slightly towards chlorine. Yes, therefore partial negative charge, and here partial positive charge. Understanding? Are you all getting it? Okay, so let us see what is being explained in our slide. Non-polar covalent bonds. When the atoms joined by covalent bond are same, like H2, O2, Cl2, the shared pairs of the electrons is equally attracted by the two atoms. It is equally attracted by the two atoms. And thus the shared electron pair is equidistant to both of them. Alternatively, we can say that it lies exactly in the center of the bonding atoms. As the result, no poles are developed, no signs, no charges are developed. And the bond is called non-polar covalent bond. Yes or no? And the corresponding molecules are known as non-polar covalent molecules. So H2, you can see here. So this electron pair, it is present exactly in between the two atoms. Can you see here? It is present exactly in between. Because it will be equidistant from both the atoms. Chlorine molecule, similar atoms, so bond pair. This is bond pair. It is present exactly in the center. So oxygen, so hydrogen. Can you see this? It is present here. Chlorine, can you see here? It is present here. Oxygen, There are two bond pairs. They are present exactly at the center. They are equidistant from the nuclei of both the atoms. Nitrogen, 3 bonds. 1, 2, 3. Triple bond it is. They are exactly at the center. Such molecules are called what? They are called non-polar covalent compounds. Non-polar covalent compounds. Yes or no? Yes. Okay. So when this polarity comes into context, then polar covalent compounds. When covalent bonds are formed between different atoms of different electronegativities, shared electron pairs between the two atoms get displaced towards highly electronegative atom. In example, in HCl molecule, since electronegativity of chlorine is high as compared to hydrogen, thus the shared electron pair, this electron pair I'm talking about, is displaced more towards chlorine atom. Thus chlorine atom will acquire a partial negative charge. Why it will acquire a partial negative charge? Because electron pair is displaced more towards chlorine, due to which electron density is slightly more on chlorine. That slight more thing is denoted by partial charge, partial negative charge, delta minus. And hydrogen atom have a partial positive charge denoted by delta plus, with the magnitude of charge same as on chlorination. Such covalent bond is called polar covalent bond. So can you see here? It is polar covalent. Greater the difference in electronegativity of the bonding atoms, more will be the polarity. So if I compare HF with HCl, fluorine is more electronegative, so that will have more partial negative charge, and this will have less. Compare HCl and HBr, chlorine is more electronegative, so that will have more partial negative charge. Understanding? Getting my point? So polarity of the molecules, the bond or molecular polarities depends on what? It depends on electronegativities of the atoms or molecules. It depends on the electronegativities of the atoms or molecules. A molecule is basically said to be either polar molecule, non-polar molecule, or ionic. So polar molecule means what? A polar molecule is usually formed when one end of the molecule is said to possess more number of positive charges, whereas other end is said to have more negative charges, creating an electrical pole. When molecule is said to have polar bond, then the center of the negative charge will be on one side, whereas the center of positive charge will be on the other. That time there will be partial positive and partial negative charges created, as in case of HCl. Yes, an entire molecule will be polar. Non-polar molecules. A molecule which does not have the charges present at the ends, due to the reason that electrons are finely distributed. When they are finely distributed, when the atom's electronegativity difference is 0. Yes or no? It's finely distributed, and those which symmetrically cancel out the others are said to be non-polar molecules. In a solution, a polar molecule cannot be mixed with non-polar molecule. Example, water and oil. Can you mix water and oil? So in this solution, water is polar, whereas oil behaves as non-polar. So these two molecules do not form a solution. Understanding? Polar substances dissolve in polar solvents. Non-polar substances dissolve in non-polar solvents. Getting my point? Understanding? Getting? So it depends upon the electronegativities. It depends on the electronegativities. Okay. Fine. So greater the difference in electronegativity of the bonding atoms, more will be the polarity of the bond. And here we have. Coming to the next one, that is dipole moment. What is dipole moment? Okay, fine. When does this concept of dipole moment comes? Due to polarity, polar molecules are also known as dipole molecules. Dipole means what? Dipole means two poles, positive and negative. And that comes only when polarity is there, yes or no? Can I express this dipole polarity or dipole moment, dipole in non-polar molecules? No, there is no polarity only. How can I explain it? Okay, so when there is separation, or I can say when there is a dipole moment arises in a system, when there is separation of charge. Please do remember this. When does this dipole moment arises? When there is separation of charge. And what do you mean by separation of charge? There is a dipole. Dipole means separation of charge. They can therefore arise in ionic bonds as well as in covalent bonds. Where covalent bonds? Covalent bonds which are polar. So in polar covalent bonds also, this dipole moment can be expressed. So dipole moments occur, they occur due to difference in electronegativity between the two atoms. Yes. So when we speak about dipole moment, we come across so many things here. When I speak about dipole moment, see here, a bond dipole moment, it is a measure of a bond dipole moment. It is a measure of polarity of a bond. Yes, it is a measure of polarity of a bond, that is separation of charges between the two atoms. It involves the concept of electric dipole moment, which is a measure of separation of positive and negative charges. This dipole moment, it is a vector quantity. What it is? A vector quantity. Vector, scalar and vector quantities we have. Scalar and vector quantities. Scalar quantities are those which have only magnitude. Vector quantities are those which have magnitude and direction. Dipole moment is a vector quantity. It is a vector quantity. That means it is having magnitude as well as direction. It is having magnitude as well as direction. I'll give you a simple example to make you all understand this concept. Okay. Let us consider a polar covalent molecule, which is that it is HCl. Now you know that chlorine is more electronegative. Therefore, the shared pair of electrons are attracted more towards chlorine, due to which slight electron density is more on chlorine. Therefore, this will have partial negative charge and this will have partial positive charge. So how do you represent this polarity? It is towards chlorine, right? Therefore, I represent it like this with the arrow mark towards chlorine. And there is a positive sign at the tail. Positive sign means there is less electron density at the tail. So this arrow mark is used to denote dipole moment. So we denote it like this. Towards more electronegative atom and a positive sign at the tail, which means there is electron density less here. Yes. So is it not? It is having some value. We can calculate it. There is a formula to calculate. Is it not having direction also? Yes, it is showing in which direction. Understanding. Therefore, dipole moment is a vector quantity. It has both magnitude as well as direction. And this delta plus and delta minus represent what? They represent the partial charges which arise due to difference in the electronegativities. Okay. Now, what are certain points in dipole moment? So how do we define this dipole moment? Let us see what is there in our slide. Dipole moment is defined as the product of magnitude of positive or negative charge, that is Q, and the distance between the charges. It is the product of. So dipole moment denoted by symbol mu. Yes, denoted by symbol mu. It is the product of charges, magnitude of positive or negative charge, which is denoted as Q, and the distance of between the charges, that is distance of separation, small d. So the formula for dipole moment is mu is equal to, you can write capital Q or you can write small q into d. So Q stands for charges, whether it is positive or negative, and D stands for distance of separation. So when we say charges, what is the unit? It is coulomb. Distance of separation is meter. So the SI unit is what? Coulomb meter, but it is measured, it is expressed in D by units. It is expressed in D by units, written as capital D. And 1 dBi is equal to 3.33564 into 10 raised to minus 30 coulomb meters. This is the conversion factor. It is the conversion factor. So SI unit is coulomb meter, but dBi unit is most commonly used. Dipole moment is a vector quantity. That means it is having some value. When you calculate it, you will get the value. And even it is having direction. In which direction there is the negative charge more, electron density is more, in which direction? How do you indicate it? It is depicted by a small arrow with a tail on positive center and head pointing towards the negative center. For example, HF. So head pointing towards the electronegative center. This is delta minus. This is delta plus. So you have an arrow, a head pointing towards negative center and a tail with a positive charge at the positive center. Yes, with the help of dipole moment, degree of polarity of the bonds can be expressed. You can express the degree of polarity of the bonds. How can we express that? Okay, I'll take examples. We'll consider few of the examples. Okay. Let me speak about dipole moment denoted as mu in simple molecules, BeF2. You know how to write the structure for beryllium fluoride. By Lewis structure, the structure of beryllium fluoride is BeF and F here. So this is BeF2 molecule. Okay. Now, when I want to indicate the, okay, I will take this. I want to indicate where which is more. Let us see how to indicate dipole moment here. Okay. Looking at the molecule itself, it is polar molecule. I cannot say it will have some certain dipole moment. Okay. Remember that. Even if the molecule is polar, it depends upon the measurement of the dipole moment. How much dipole moment is there? Now see, if you consider this bond, there are two bonds, right? I'll consider this bond. Fluorine is more electronegative. Therefore, how do I show the dipole moment? I will show dipole moment like this. Correct? Towards fluorine. And here, if you consider this bond, again, fluorine is electronegative. So I will show the bond like this towards fluorine and positive charge on the near the beryllium atom. Yes or no? Because there is a slight negative charge on fluorine being more electronegative, slight positive charge, slight negative charge. Understanding? So I will show dipole moment like this. Since dipole moment is a vector quantity, these are in opposite directions. Both the dipole moments are in opposite directions. Yes, both the moments are in opposite directions. They are equal. Both the dipole moments, they are equal. Bond dipoles, we say, bond dipole moments, they are equal in magnitude. They are equal in magnitude, that is value. But what? Opposite in direction. Correct. So one is taken as plus, another one is taken as minus. Therefore, what will be the net dipole? The net dipole will cancel out each other. Yes or no? So the net dipole of BeF2 molecule will be what? It will be 0 because both the dipoles cancel out. Both the dipoles cancel out. Is that clear? So net dipole will be 0. Similarly, you consider water molecule. Dipole moment in, let us take carbon dioxide, CO2. Carbon dioxide is written like this. We have seen Lewis structure of representing carbon dioxide. You know that oxygen is more electronegative. Therefore, I will show the dipole moment like this. Polarity here, it is shown like this. Correct.